Hello everyone, welcome to the lab demonstration for CIVE 250 structural analysis. In this video, I'll walk you through the experiment setup, what you'll need to do before coming to the lab, and also the steps you'll need to do within the lab session to complete the experiment. You will have 50 minutes to complete the experiment, and that's quite enough if you are familiar with the steps. So let's get started. In this lab, you will be doing a beam bending analysis. First, you will measure the reaction force of supports as a load is moving along the beam, and that's what you know as influence lines. Next, you will load the beam under various loading conditions and measure its deflected shape. Then you'll have the chance to compare your experimental results with your analytical calculations and elaborate on them. So the apparatus, it consists of a simply supported beam. It's supported with magnetic pin right here and just sits on the roller support over there. It's a 3/4 inch wide, 1/8 inch thick, and 4 foot long beam. And it's placed along its weak axis as you see here, so the deformation under the loads that you'll apply be observable for you. There are magnetic hooks attached along the beam, and they're there for you to place loads on them. So you'll be given 2 sets of loads that each consist of 10 separate 100-gram weights. The apparatus consists of 2 load cells to measure the reaction forces of the supports, 1 displacement transducer, and it allows you to measure the deflection, the vertical deflection of the beam as it bends under loads you apply, and a position transducer, and that allows you to measure the exact position of the point you're measuring the vertical deflection. It's an ultrasonic sensor, so it constantly creates ultrasonic pulses. Based on the travel time of the wave, it calculates its distance. So the apparatus is connected to the Pasco Universal Interface. You might be familiar with this unit from your previous labs. It is a data acquisition unit, and it allows to read the sensor measurements through the Pasco capstone software in your computer system. So we'd like you to have the Pasco capstone software pre-installed on your computer before you come to the lab. One thing to mention that the position transducer connects to your computer with Bluetooth, so make sure that the computer you bring has Bluetooth capabilities. Additionally, don't forget to disable the sleep mode of your computer system before you run the experiment, as it can interrupt the communication with hardware. And finally, if your computer system does not have USB port, make sure to bring a USB legacy adapter with you to the lab. That's all. Now let's get started with the experiment. So the first part of the experiment, as I mentioned, is calculating the influence lines. But before doing that, you'll need to calibrate load cells. Why do you do that? Well, load cells are measuring voltage readings. Those voltage readings need to be correctly translated, converted into force values that represent the reaction forces. So calibration means, as we go along, I'll explain that. So you might start with connecting the Pasco capstone. Open the Pasco capstone software on your computer. Select sensor data and select manual sampling. In manual sampling, the sensor data will be constantly read, but you have the option to keep that data to write it into the output file as often as you want. First, make sure that the hardware is connected to your computer. If it is not turned on, turn on the wireless motion. Okay, so the displacement sensor and wireless motion should be automatically detected. Make sure that your computer is connected to the correct wireless device by controlling the number right here. The number right here with the number written on the device on your apparatus. For load cells, you will need to add them. So select channel A, type V. It'll bring voltage sensor. Select voltage sensor and do the same for channel B. Now you have 4 sensor readouts. Right here, select common rate, so it will allow you to change the frequency of sensor readings at whatever rate you want. Set it to 5 Hz. You can select the first column of the table and set it to voltage of channel A and the second column to voltage of channel B. Alright, now make sure that the displacement transducer is not touching the beam and the beam is placed correctly. Start to reading data by hitting this preview button. You'll see that some voltage readouts show here for channel A and B. As it is running, open hardware setup. As you're reading the voltage values, select this little gear right here beside channel A and zero the sensor. Now do the same for channel B. You'll see that the voltage readings are almost close to 0. At this point, you wanna put a 1 kilogram load on support A. The voltage reading will change. Keep that value. Bring the load and put it on support B. And keep that value as well. So you will need to convert these voltage readings into force using this formula given in your lab manual. In the manual, there is a sample voltage reading here. You will replace that with whatever you are reading during the experiment at that moment. So for reaction of support A, introduce this equation in calculator. Open the calculator, define the parameter that you want to represent the reaction force, and type that formula. 1 divided by minus what you read for voltage of channel A was 0.221. So write that number here, minus 0.221 multiplied by, as you see in the lab manual, voltage reading of that channel. So if you want to call a reading, a sensor reading, open a bracket and it will bring all of the possible readings that you can select. Select voltage of channel A and that's all. Now for support B, do the same thing. 1 divided by, the voltage you read was 0.218. Minus 0.218 multiplied by, open a bracket, square bracket, and select channel B. That's all. Now if you select the reaction forces to show on the table, you can select if you've calibrated correctly by reading it again, place the weight on support 1 and it'll show 1 kilogram on support A and 0 on support B. And if you do the same for support B, it'll show the other way around. Also, let's set the units here. What you're reading is kgf. All good. Now you've calibrated the load cells. You might start doing the influence line test. You will place the weight along the beam on supports and hang them from the hooks, and at each point you will keep the samples. So on support A, keep sample, move it to the first hook, keep a sample, move it to the next hook, we're in support B now. And finally, the last hook. That's all. You can stop reading and plot the influence line, moving the data into an Excel file. Right after you did every step, don't forget to remove the weights, because we don't want the weights be hanging for too long from the beam. It can create some permanent deformation shapes. All right, now we can move to case 2, where we are measuring the deflected shape of the beam. We will load the beam and measure at each point where is the vertical location of the beam. But the beam, at its very unloaded shape now, it might not be completely a straight line. It might have already been deflected by its own weight, by the weights of the hangers. So the first step is to measure the initial shape of the beam. Yeah, to do that, you will first need to move the position transducer at the 30 centimeter marking, which is support A. You can loosen up a little bit of this transducer and locate it on the beam, a little maybe dented, so it have place to move up and down. While you're here, zero this sensor by toggling the on it, and you also want to zero the position transducer. You're doing that right here, just as you did with a voltage sensor. Select this little gear beside wireless motion. Scroll down a little bit to find zero sensor now. And okay. You may want to open a new page right here. It asks for a desired layout. You can just select this one. We want to have a table with 4 columns. One showing the reaction of A, reaction of B, position, and the displacement. On the chart, select position for the horizontal axis and displacement for the vertical axis. You can set the units to centimeter for position and millimeter for displacement. All right, start to preview. So every 5 centimeter, keep a sample. So while you're on the support, keep a sample. Now move the transducer to 5 centimeters to the right. Keep a sample. Be a little careful with moving the sensor. You will want to handle the column mostly from the bottom and just support with your hand from the top. Meanwhile, you should be able to hear the ultrasonic pulses that the sensor is sending. So be mindful your hand does not interrupt the distance between the sensor and the column that you're moving. You should be able to see the shape of the deformed beam on the graph that is plotting, and it is just like the deformed shape of the beam, but as you're moving along, you can see that on support B, it read 0, which is reasonable because it's a support, so means that it's just a little validation. And as you're seeing, without any loads, the beam is not quite straight. Although little, it has some deformation, which you want to account for when you loaded the beam later. This deformation will still gonna be there, so you want to deduct whatever you're reading now from your measurements in the next step. All right, this is the initial deformed shape of the beam now without any loads. The next step is trying out different loading conditions that is stated in a lab manual and repeating the same steps. Just to remember that this is the reference point of the beam and must be accounted for when you're calculating the final results. So you need to deduct these values from whatever you're testing in the next steps. Because it's all the same steps, I'm not going through the next steps. You'll be doing the same in the lab with some loads. And that concludes the demo. Good luck with the lab and see you soon.